Now that we're through the first 4 steps of hypothesis testing, the last 2 steps go actually very quickly. We spent a lot of time on step 4 because we really want to designate that area that we're going to reject the null hypothesis. So let's just say that we're going to use an alpha of 0.05 if that's the case, and we have a two-tailed test, which is what we were assuming in this particular scenario. Then that means that we have z-statistics of plus or minus 1.96. And so if we have values that exceed negative 1.96 or positive 1.96 for a z-statistic, then we will reject the null. If it falls someplace in between those two values, then we fail to reject the null hypothesis. So let's go on to step number 5. Let's calculate our test statistic. Now, if you remember from the scenario, we said that all employees with the old training had a mean of 72 with a standard deviation of 12. And then remember that we took that standard deviation and we turned it into a standard error, and that standard error was 2.19. Now, let's say we conduct our new training and of our randomly selected 30 employees, and from those 30 employees we get a performance rating of 76 with a standard deviation of 10. Now, what's important to note here that this is a sample, and so all we're really looking for here from the sample is the mean of 76. Because we have a standard deviation in the population, we actually don't care about the standard deviation for the sample here. There's no reason to estimate the standard deviation for the population when we have the standard deviation in the population already. So we can disregard the standard deviation of 10 here because we already know in the population the standard deviation is 12. And so what we gain from here is a mean of 76 for performance appraisal ratings, and for our employees with the new training, and we want to compare that to the performance with the old training. And as I mentioned on the previous slide, we already calculated our standard error. Our standard error is 2.19. So here's our z-statistic formula. Notice that we're going to take the mean of the sample, we're going to subtract the mean of the population. So in other words, we're going to take the new training, mean for performance for the new training, and we'll subtract the mean for performance in the population with the old training, and we'll divide by our measure of variability by our measure of standard error. In other words, our standard error gives us the variability due to chance based on the very different employees that we have within our organization. So we plug in those numbers and we get 76 minus 72. So performance with the new training is 76. We always start with the mean of our sample. We then subtract the mean of the population, which was 72, and we divide by our standard error of 2.19. That gives us a z-statistic of 1.83. So we can take that z-statistic, our test statistic, and we can now make a statistical decision. Remember, a statistical decision is when we take our calculations and we use our calculations and only our calculations to make a decision. So let's go back and let's look at our null and our research hypothesis. The null hypothesis is that there's no difference in performance of Applebee's employees between the new and the old training programs. The research hypothesis is that there is a difference. Now remember, we had an alpha of 0.05, and so our z critical, so the point that if we exceed, we will reject the null hypothesis, is plus or minus 1.96. We ended up with a z-statistic of 1.83. That does not exceed our z critical value of 1.96, so in this particular case we would say we fail to reject the null hypothesis. In other words, we fail to reject that there's no difference in performance between the two training programs. We find support that these two training programs seem very similar to each other, and they're no different at a greater than chance level. So again, when we say we fail to reject the null, we fail to reject it, that means we're finding support for the null hypothesis. There appears to be no difference in performance between our two training programs when it comes to our employees. That means we can cross out our research hypothesis saying that there is a difference. So we did not find support for saying there's a difference between the two programs. Remember, we failed to reject the null, and so therefore we find support for the null hypothesis, not for the research hypothesis. We can demonstrate our statistical decision visually. So here is our normal distribution. You'll notice that we have our cutoffs at an alpha of 0.05. So again, it's two tails, so we divide our alpha by 2. We get an alpha of 0.025 in each tail. The corresponding z-statistic is 1.96 in the positive direction and negative 1.96 in the negative direction. So you'll see that the region between those two critical values is our fail to reject the null region. Essentially what we're saying is that there's no difference between the two training programs. And then you see in the two extreme tails we have reject the null, in the negative direction, or reject the null in the positive direction. And notice that those are shaded regions, those are our critical regions, that if our z statistic from our test falls within those regions, we will reject the null hypothesis. In this particular case, if you look at the blue line, that is our z statistic that we calculated from our test, a z of 1.83. That did not fall within the critical regions. It did not fall in the tails and the extreme regions of our distribution. It fell in the middle between our two critical values. And so therefore our decision is to fail to reject the null. It appears the new training is no different than the old training. Now you should also note that at a z of 1.83, that the percent of the population is greater than 2.5%. Remember, we set our alpha in the positive direction at 2.5%, so the probability is greater than 2.5%. And so again, that means that our chance is higher than a 2.5% chance in the positive direction. And so we would again reject the null. We would say in this case there appears to be no difference. So even though there's a numerical difference, performance appraisal of 76 versus performance appraisal of 72, there's a difference between those two means. But because of the variability, or standard error of 2.19, that difference was not at a greater than chance level. We would say that these two programs compare statistically to be very similar to each other, and at least not at a greater than chance level. Now let's say, because the researcher gets to decide what alpha is, now let's say that our overall alpha was 0.10, or a 10% chance for a type 1 error, saying there's a difference when there isn't one there. And so notice that our critical regions got larger, that our two critical values got closer together here. So now we have a z statistic of 1.65 and negative 1.65 for our cutoffs. If we look at our z statistic that we calculated based on our sample, we had a z statistic of 1.83. So note here that that would fall within our critical region. So had we started off with our test with an alpha of 0.10, then we would have rejected the null hypothesis. We would have rejected that there was no difference, and we would conclude that it appears that the new training program results in higher performance than the old training program. So because the researcher gets to decide alpha, there is some subjectivity to the particular hypothesis test that we run when we set up those critical values. Now of course, if we do set our alpha at 0.10, we increase our chance of being wrong. So we increase it from 5% chance of being wrong to a 10% chance of being wrong. And so that is a disadvantage. So it's more likely that we'll find a difference if we increase alpha, but at the same time our chance of finding that alpha due to error increases as well. And so usually we want to be more conservative than the more strict, but just realize where we set our critical value can influence our statistical decision, whether we reject or fail to reject the null hypothesis. Now let's go ahead and revert back to the alpha that we began the particular study with our context. We said we wanted to use an alpha of 0.05, and so here it is visually, alpha 0.05. So notice that our z statistic of 1.83 does not fall within the regions where we would reject the null hypothesis. It falls between our two critical values where we will fail to reject the null hypothesis. And so we're concluding that there appears to be no difference between the two training programs. So that was our statistical decision. We still have one more step, step number 7, which is our practical decision. Now our practical decision is what we would actually do in real life or in practice. And so I don't really care so much what you say for your practical decision, as long as you make a decision and then support it with the evidences that you have collected. So in this case, our question is whether or not we should implement this new training. And so certainly one of those pieces of evidence is our hypothesis test, the fact that we failed to reject the null hypothesis. We found that there was no difference between the new and the old training program. However, there are other factors that are important to our decision. One of those factors is the reliability and validity of the measurements themselves. And so we measured performance, and it was measured on a 0 to 100 scale, where higher scores meant higher performance, but we really didn't operationally define what performance was, or how it was specifically measured. So we could probably assume that the ratings came from supervisors of the employees. And so if they came from the supervisors, there could be a subjective component to that rating. So supervisors may not actually observe their employees all the time. So if you think about it, supervisors have many employees, and so not always observing their employees. They only see them for a certain portion of the day. And so they don't see all of their activities. And so that may lead to some subjectivity in responding. Additionally, supervisors may have favorite employees that they may rate higher, not because they perform better, but just because they like them more. So another factor might be the assumptions. And so we want to look at them and see how well did we meet each of those assumptions. So if you remember from Thursday, we look at our 4 assumptions for a z-test. We actually did a pretty good job. We either could assume or did meet each of those 4 assumptions. And so we might have a certain level of validity, or there might be a certain level of validity when it comes to our statistical decision, that we weren't worried about some of the limitations that come with not meeting our assumptions. Another factor that may be important might be whether or not the savings is greater than the costs. And so even though we didn't find an increase in performance, if this new training is cheaper, if it saves the organization money when it comes to training dollars or payroll, then we may still want to implement the training even though we didn't find a difference between the new and the old training program. Maybe another factor is how technical is the training. If this new training is very technical, then maybe we don't implement it. If it's less technical than the current training, then maybe we consider implementing the new training anyway. And of course, another factor that may be important also is the mission and vision of the organization. So what is it that the organization values? And so if it's Applebee's and they value customer service, and this new training program will increase customer service, even though it may not increase performance, then we may still want to implement this new training even though we failed to reject the null hypothesis. Even though we found that there was no difference in performance with the two types of training, the new and the old, but if it increases customer service, which we value, which is important to our organization, then we may still implement this new training. So what I'm really trying to say here is that with your practical decision, it doesn't matter if you say yes, we should implement, or no, we shouldn't implement. What I'm looking for is what is your argument given the evidences that we have collected. Congratulations, you just completed your first hypothesis test. So one of many that you'll learn this particular semester. Each hypothesis test that we learn after this will follow the basic format that we just covered. There'll be some changes here and there. Now, of course, we're not completely done with z-tests yet. We still need to talk about effect sizes and confidence intervals and power. But for the most part, we've covered what a hypothesis test covers. So we'll cover those next topics in the next lecture, and I'll see you in class.